Hey friends, let's continue the conversation about pharmacodynamics. So, drug therapy only modifies natural processes. So, you take blood pressure medication to lower your blood pressure, but there are natural ways that the body lowers blood pressure. For example, they might reduce the amount of aldosterone, but in somebody with like chronically high blood pressure, they're unable to do it. So the process is there, the body's just not able to do it. So drugs help. They interact via the electrostatic bonds, which is the most common way they interact. Covalent, which is the strongest, via hydrogen bonding, and the van der Waals forces. They can stimulate, depress, or they can replace a certain like hormone that we're missing. They can also induce cytotoxicity, such as like chemo drugs or antibacterial drugs. And the drugs work via physical, chemical, or via enzymes or receptors. So let's work through that. The physical actions, it's basically like, absorptive properties, or just the mass of the drugs itself, such as bulk laxatives. Like it will just flush you out just from the sheer amount of medication that you take. So something like magnesium citrate, like you take a lot of it, or propylene glycol. There's the osmotic effect, which is mannitol, so it will draw the water out, like just physically, due to its own properties. And then the radiopacity used in contrast media. Chemical action, they neutralize the effect of whatever toxins via the chemical properties or during competition or chelation. Via enzymes, there is, of course, the competitive, so you got to know this, competitive, non-competitive. A competitive enzyme can be reversible. You overcome it by adding more of the substrate. It works on the same site. The Vmax is the same. So in the Line-Weaver-Burke plot, the Vmax is the same. But the x-intercept will like go closer to 0 and the slope increases, but the y-intercept is the same. In an irreversible enzyme, there is going to be the Vmax decreasing, and in a non-competitive enzyme, it works via the allosteric site. The Vmax will decrease, but the Km will stay the same. So, and the x-intercept will be the same. So you can see here, this is going to be the Line-Weaver-Burke plot. This is the Michaelis-Menten. The Michaelis-Menten is different because it kind of shows how saturable things are. So in a competitive inhibitor, it's like the same Vmax, so it could be saturated the same. Via non-competitive inhibitor, it takes less to be saturated. So, like I said, saturation occurs. Km is going to be inversely related to affinity. So the higher the Km, the lower the affinity. And the lower the Km, the higher the affinity. So, of course, it's easier to be saturated, right? The Vmax is going to be directly proportional. Line-Weaver-Burke plot, you want to look at the Vmax and the Km, but unlike the Michaelis-Menten, where the lower the Km, or the lower the curve, like the higher the affinity, it's going to work on the you're going to focus on the y and the x-intercept. So the decreasing the y-intercept will decrease the Vmax, and the further the x-intercept is, the greater the Km and the lower the affinity. So it's still an inverse relationship, but like you said, the further the x-intercept is, the greater the Km. So drugs work via the a specific macromolecule component of the cell that binds to and interacts with the drug molecules. There's like two theories, the lock and the key versus the induced fit. There's the agonist that, amplifies a reaction, antagonist, which like stops the reaction. It doesn't necessarily work against, like, the agonist, is not making the opposite effects. It's just stopping whatever the agonist effect is. The inverse agonist will activate a receptor that produces the opposite agonist effect. So that's the difference. Partial agonist, of course, it just produces a maximal effect. So the intrinsic ability of a drug is the ability to induce a conformational change, and that is the induced fit model. So the agonist minus affinity plus the intrinsic activity is going to be like the formula you need to concentrate on, because when IA is equal to 1, that's the full agonist, and when it's less than 1 is going to be the partial agonist, and when it is 0, it's the antagonist. So inverse agonist is going to be theoretical. There is no such drug that like just completely does the opposite effect of a agonist. So there's no such thing as a high blood pressure drug, or a drug that raises blood pressure via opposite action of the other anti-hypertension drugs. So an agonist plus an allosteric activator will increase the responses the most. An agonist plus a competitive inhibitor, of course, has the same Vmax, but you need higher doses. An agonist plus a non-competitive inhibitor, you need a much lower dose, lower Vmax, because remember the Km is lower too. So there's the systems that or the signaling pathways that I have to worry about. So it's amplification of the signal, integration of the signal into the cell, transduction of the drug receptor interaction as the signal, and then the translation of the receptor activation into functional response, which means that once the signal comes in, the proteins is going to be translated so the receptor can be brought to the cell membrane. There are the G protein coupled pathways, which are metabotropic, so it requires some time to work, and ADP, or ATP, I'm sorry. So this is the ADP, ADMP, phospholipase C, ion channels, the JAK-STAT receptors, and it has a role to play in transcription and protein production. And then the transmembrane enzymatic receptors is going to be a tyrosine kinase, and the intracellular receptor is going to be ligand gated, and that's the ionotropic. So this is going to be like instant, and it requires the gradient, electrochemical gradient. So most all of everything is going to be enzyme linked. So the G protein coupled receptors, there's a bunch. GS, the stimulatory protein, is going to use CAMP. GQ is going to require phospholipase C. G0 is going to be calcium channels, and GI inhibition is going to be inhibiting adenyl cyclase or opening of the potassium channels to induce hyperpolarization. So the metabotropic G proteins is going to be like this squiggly line, or a 7 kind of membrane spanning helical structure. It's heterotropic, and the agonist binding site is extracellular on the outside, and the alpha beta gamma binding site, sorry, you spelled that wrong, is going to be on the third loop between the 5th and the 6th helixes. And then let's see, the G protein will bind to that site and then activate, and adenyl cyclase will produce the ATP, or use the ATP to produce the CAMP, and then protein kinase A, and then phosphorylate the protein, and then the cellular response. Inotropic is like this like flower kind of view. The alpha subunit is going to be the agonist binding site. The transmembrane enzymatic receptor, there's going to be like extracellular and intracellular units. It's only one. And the intrinsic catalytic domain you have to remember is tyrosine kinase. JAK-STAT is going to be one of the examples. There is no intrinsic catalytic domain. There's no enzymatic function, so things need to bind to it in order for it to be phosphorylated. JAK floating around will bind, and then it will dimerize the protein. And then these two will phosphorylate each other. STAT will bind, more phosphorylation and dimerization, and then STAT will go into the nucleus. And then from there, it binds to the zinc fingers and activate transcription. These are the aberrations that affect this pathway. So polycythemia vera, thrombocythemia, primary myelofibrosis, and like tumor cells. The transmembrane enzymatic receptor, it has enzymatic protein kinase, so it doesn't need JAK to like actually bind. And same kind of process, but it doesn't have like the two-step process. So insulin is one of the examples. Intracellular receptors will regulate gene expression, of course. This protein, HSP90, will stabilize the drug binding when it is bound, and the carboxy terminal is where the drugs are bound. Zinc fingers will be dimerized, and complex goes into nucleus to activate or inhibit transcription. Steroid hormones use this path. So there's either upregulation or downregulation, and over time, of course, drug usage will result in desensitization. Spare receptors are going to be spare if they are able to elicit like a maximal biologic response, even if like if less than 100% of the receptors are activated. So kind of like I don't know, let's just use warfarin, and if you give warfarin, it's a very, very effective drug. It has a very low therapeutic index, so it only requires a little bit to be effective, and that definitely means that 100% of the receptors are not activated. So let's say maybe 20% is activated, but it still maximizes maximal biologic response, so it kind of responds to the receptors that are spare. So a dose rate is going to be a hyperbolic curve. Log dose is going to be a sigmoidal, and when you look at the two together, this particular one doesn't have it right now, but imagine that there's like a hyperbolic curve. There's going to be a wide range of drug doses, and you can compare between the agonist and antagonist. That kind of shows the quantal, which is an R none response or a graded response. So it's just some definitions. Median lethal dose is amount of drug that causes death in 50% of the sample. Median toxic dose is the dose that causes toxicity in 50% of the sample. The median effective dose is the dose making the desired effect in 50% of the sample. And the effective concentration is the plasma concentration of the drug that produces 50% of the maximal response. And the effective dose is going to be the maximal response, or the dose that makes the maximal response. Potency is the amount of drug needed to produce a given response, so it's relative. And the efficacy is the maximum response that can be produced by the drug. The drugs can have the same efficacy but different potency, and the more potent drug, you need less of it. So if you look at the graph, the potency difference is going to be XY, efficacy is going to be a higher, sorry, I'm blanking here, it's going to depend on the y-intercept. So if you can have, like, let's say the same efficacy but different potency, so let's say like A is on this side right here, and it's at the same height as efficacy, you would say these drugs will have the same efficacy, but drug A would be more potent because it's closer to 0. Selectivity, same response to same drug with 2 responses because of the specificity of the receptors, such as beta blockers. Remember, beta blocker will block either like alpha or beta receptors. That's selectivity. I'm sorry. Specificity is the range of action produced by only one drug. So it depends on whether the drug was given it acts on single or many receptors and how widely the target is distributed. So the therapeutic index is going to be the median dose divided by the median effective dose, or the median lethal dose divided by the median effective dose. And the higher the therapeutic index, the safer the drug. Like right here. So it's between like the therapeutic window and the toxic. The therapeutic range or window is going to be the minimum therapeutic effect and the maximum acceptable adverse effects. So it's going to depend on the drug, of course, and the concentration of the drug in plasma. So synergism of the drug is going to be the most dangerous, of course, because of the additive effect. Super additive effects is different from just plain old additive effects. So additive is just the effects of drug A and B together. Super additive is the drug of these drugs together, effects of drug A and B together, and it's greater than the effect of this by itself plus the effect of this by itself. Antagonism is going to be the opposite effect. It's going to be less than, and physiologically it's going to be selectivity and competition. That's it for now. Thank you for your attention and good luck studying.